How's it going, everybody? And welcome back to our Cisco Enterprise series, where we're going to be focusing on EIGRP best path selection. So this is going to be important regardless of how simple or how complex your EIGRP implementation is going to be. So when I say simple, it could be, you're just turning EIGRP on for a handful of subnets, and then you've done your due diligence of doing your best with making sure that you have, consistent gig, 10 gig, or 40 gig connectivity, stuff like that. So the reality of it is, unless you're in a core data center where you're dealing with like a VXLAN fabric or an ACI fabric, where you're going to have, or data center specific communication where you have a lot of east-west communication, and bandwidth can be a premium in the data center, where you're typically going to have a lot of high-speed connectivity. You're going to have some level of routing in there, but the reality of it is, beyond that, when you're in the LAN and stuff like that, you're not going to have, usually, you're not going to have those high speeds, 40 and 100 gig. You're not going to have that in the LAN. That's going to be more data center specific. Where in the local area network, right, depending on how complex that is, you could very easily have 10 gig uplink, 25 gig uplink, stuff like that. But a lot of your downstream connectivity to your end users, that's going to be gig. You might have a little bit of 10 gig going on and stuff like that, but most of the time it's going to be 1 gig, and you're going to have 10 gig in infrastructure. So as long as your infrastructure connectivity is going to be a consistent bandwidth, 10 gig and stuff like that, then the path selection is not going to be very difficult. What you and I are going to walk through and talk about is going to be how EIGRP figures out how to come up with this composite metric. That's what we're going to go through. Now, I will tell you that I'll scroll down here a little bit. There are some very intense math, some rather intense math that you can get into, where it will get into the 10 to the 7th power times 65536 da 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 10 to the 7th power times 256. There is some math involved here. However, I am not a math person. Like, I couldn't stand math in school. I can do your basic, add, subtract, multiply, divide. Excuse me. And I also have the basic understanding of how the power of 2 works, because I obviously know how to subnet with 2, 4, 8, 16, 32, etc. The real point here that I want to make sure that you guys understand is going to be the capability of how EIGRP figures out the best metric, the best path based off of the composite metrics and all the details behind that, so you understand how EIGRP does path selection. We're going to talk about the bandwidth calculation, I should say the metric calculation as well, because it is the one protocol out of all the IGP and BGP protocols that we're going to be working with that actually has 2 different variables to take into consideration. All the other variables, OSPF, IS to IS RIP, they only have one, bandwidth, and IS to IS has a metric calculation just like OSPF does. It's based off of bandwidth. So the EIGRP is the oddball protocol that takes a little bit more to understand it. But here's the reality of it. As many Cisco exams as I've taken a lot of Cisco exams, I have never once had a question pop up in front of me that has forced me to be has ever forced me to pick be able to go into a level of detail on how to figure out what the composite metric is. If you've got X, Y, Z, A, B, C variables, what is the composite metric? I've never once had that question. What it will ask, for example, on the other hand, is if we come back down here, it might ask, for example, which of these outputs, the 10 to the 7 times 256, which one of these, and they might have a couple different variations of it, is the correct bandwidth calculation? This is something that I do believe you should understand, or at least know what the calculation is, so that in the event that you have to go, a stump the chump type of question, a trivia question, as far as I'm concerned, then you might see this. I believe I might have seen this question similar to that on the CCIE written exam that I took almost 10 years ago. So let's see, I passed the CCIE written July 31st of 2014. So in that case, it's been 2014, it's been 7 months, 8 months. I'm just a little over 9 years ago I took that exam. And I remember a question similar to that being on the exam. But it was the CCIE written, right? It was all theory. So I don't expect you guys to get asked questions like that. It's more or less, how do you do it? Because you want to have a deeper understanding. Now, these are my CCIE notes, right? When I was getting into the weeds and I really wanted to understand how it worked and I was all gung-ho, you're not going to have to worry about that. I mean, at least you shouldn't have to. So this is the idea right here. If you can understand 10 to the 7th power times 256 is the actual bandwidth calculation. That's what you need to remember. So with that being said, let's go ahead and dive into this so we can understand the in-depth pieces of how it comes together. So let me go ahead and get out of the way, and we're going to walk ourselves through this as we're going along here. So choose path with lowest composite metric. So you have 4 different variables that are actually able to be used. MTU, as you can tell, isn't one of those that's ever actually used. So you have the bandwidth, which is the inverse lowest bandwidth along path in kilobits per second, scaled by 10 to the 7th by 256. The one key thing I want you to understand is it's the inverse. What does inverse mean? The opposite of the highest, right? We're not taking the highest. We're taking the lowest bandwidth. Now, why would you take the lowest bandwidth? Well, simple. Think of it like this. You're in your car and you're trying to get from point A to point B, wherever that might be. Well, you're driving along, or you get in your car. You know generally where you're trying to go, but you don't know the exact turn by turn, or at least you can get pretty close to your destination, but not exactly there. But unbeknownst to you, there's a lot of traffic in the area you're trying to go. So instead of taking all the major roads, which is what I would do, the GPS says, you know what? I'm gonna have you get off one exit sooner than your actual exit you should get off on. And I'm gonna have you come up through some side streets. And that side street is gonna be a residential street. Well, here where I live, if you're on a residential street, 25 miles per hour is as fast as you can go. So 25 miles per hour will be the slowest speed limit you'll be able to calculate against. Now, the reality of it is that that's, it sort of makes sense, but the reality of it is once you get there, your speed will dictate depending on where you are. Where in the reality of it is, if you're on an actual data transfer between point A and point B, if say 25 megabits per second is your slowest link, but your average speed is 1 gigabit, well, you can't calculate it based off of 1 gigabit. You have to calculate on 25 megabits, because unlike you getting in your car and driving somewhere, where you can adjust your speed limit based off the road you're on, where in networking you have to take into consider the entire data path. So if in the middle of your data path there is one really slow link, that's the bandwidth you have to do your calculation on. And that's why it's written the way that it is. Whatever the slowest link is the link speed. And that's between point A and point B. If it's 25 megabits per second, you're going to be doing your kilobits per second is scaled by this. Now the delay is the cumulative delay along the path in tens of microseconds scaled by 256. The delay is 100 seconds. So the calculation would be 10 tens of microseconds. So keep that in mind as well. Load is the highest load along the path. Reliability is the lowest reliability along the path. So these are just things to keep in the back of your mind when you're trying to understand how EIGRP figures out what it does. Now the metric calculation. And just to recap, the load and reliability are not used by default. These are K values that you could potentially use, but they're turned off by default. So the metric calculation. Composite metric is computed. Route with the lowest metric is the successor route. Route with the lowest end-to-end metric. This route is installed in the routing table. Successor's metric is the feasible distance. The feasible distance is going to be a combination of the where is it here? The advertised or reported distance and the local distance combined is your feasible distance. And we'll talk about that here in just a minute. Metric weighting. K values allow for manual administrative weighting. Default are K1 and K3. It implies the default composite is bandwidth and delay. You can modify the metric weights by adjusting them if you'd like to do so, but must match for adjacency to occur. All routers participating in that AES, their metrics must match. And this goes back to what I mentioned a little bit ago, or it might have been a different video, where I mentioned, unlike OSPF and IS to IS that have dedicated databases, and they only use one variable to one thing to calculate their metric. So OSPF uses a cost based off of the bandwidth, the inverse bandwidth. So it'll look at whatever the speed is end to end, and that's going to be how it calculates. Where IS has a metric calculation, so it's based off of a metric value. So I believe it's 10 by default, or no, sorry, 64. It's 64 by default. But we'll talk more about that when we get into IS to IS. The key thing is here is all the routers in your AS, the K values on every router must be the same, because if not, you're going to come up with a different calculation than another router, and therefore you might go a different path. So in order for all of the routers to give you a precise calculation, everybody needs to be on the same sheet of music, everybody needs to agree on all the same values. That will give you the best chance for a proper outcome. So terms, we have the successor, which is the best path to a destination. We have this feasible distance, is a composite metric of the best path. So it is a combination of the reported and local distance combined together gives you your feasible successor. I'm sorry, your feasible distance. Your feasible successor is a backup path to a destination. Your advertised or reported distance is a composite metric learned by your neighbor. This is the upstream router's metric for the best path. Then you have your local distance. So this is also referred to as your, this one here, the local distance is also referred to as your computed distance. Computed distance is going to be your metric to reach your local neighbor, whatever that might be. Your feasibility condition is a criteria for a valid backup path. Does this alternative path that's got a higher composite metric, does it create a loop? Do I have to go through some sort of rigmarole or a loop-de-loop or something like that in order to get to where I'm trying to go? If you create a loop, even if you create a loop, in order to get to your backup path, do you have to go through a loop in order to get there? If you do, then that therefore violates the feasibility condition, therefore it is not a valid backup path. And I'll whiteboard this out here in just a minute so you guys can see what this looks like. Path selection in detail. You have your advertised distance. Each update includes the metric the upstream router uses to reach the destination. The local distance, local router knows the metric to reach the upstream router. The advertised distance and the local distance. The best path or successor is chosen based off lowest administrative distance, lowest advertised distance and local distance. That is going to be your successor route. The feasibility condition. Once best path is chosen, additional paths are examined for backup routes. The feasibility condition finds loop-free paths via if the advertised distance is greater than the feasible distance, less than, not greater than. If the advertised distance is less than the feasible distance, meaning my neighbor's best path is less than the feasible distance, the path is loop-free and a viable backup. In other words, if your metric is lower than mine, you are closer to the destination and loop-free. Paths that meet the feasibility condition and feasible successor, only feasible successor can be used for unequal cost unequal cost load balancing. EIGRP only knows about its directly connected neighbor. All other paths are learned. So what that essentially means is, well, this is the key thing here. If your neighbor's administrative distance, if your neighbor's advertised distance is lower than your feasible distance, so your end-to-end distance, therefore it's a valid backup path. So let's whiteboard this out real quick, just so we have a visual that makes sense. Grab my pen tool out real quick. So let's say we have R1, we have R2, we have R3, we have R4, we have R5, we have R6, R7, we have R8, we have R9, and we have R10. So we'll just draw this out real quick. Put a bunch of lines together. So let's assume that we are trying to get from point A to point B. Let's say R1 and R8 have users attached to them. R2, 5, 6, all these other guys in the middle, they're just transit routers. There's no users directly attached to them. What will end up happening is we have to look at this in terms of how many hops. So let's assume, just for the sake of argument, that every one of these interfaces is 1 gig, and the delay is 100. So it's 10 tens of microseconds. Okay? The 100 delay. Something simple like that. Which means across the board, we have the exact same composite metric, right? We're going to get to everybody's going to see everything the same way. So what we're going to do is we're going to say, if I'm trying to get from R1 to R8, what is the shortest path to there? Well, we got 1 hop, 2 hop, 3 hop, 4 hop. Then we have, this is 1 hop, then we have 2 hop, 3 hop, 4 hop, 5 hop. Then we have, this would be potentially 1, 2, 3. This could be or 1, 2, 3. This could be a 4 hop. This could be a 5th hop. So let me ask you this. The first path, R1, 2, 5, 6 to 8, would this be considered your feasible successor or your successor? Well, this path, so 1, 2, 5, 6, and 8, this would be equal to your successor. Okay, and the reason why is because it's 1, 2, 3, 4 hops away. Because we're for the advertised distance. That's how we're calculating this. Now, from a backup path, so we've already calculated that the 1, 2, 5, 6, 8 is the successor. What is 1, 2, 3, 4, 7, 8? So we got 1, 2, 3, 4, 7, 8. What would that be? Well, that's 6 hops, right? But it's this would be your feasible successor. Now, how would that be determined? How would you switch from your successor route to your feasible successor route? Well, that's simple, right? As long as the connection between R1 and R2 is solid, then if something happened to the connection between R2 and 5, or R5 and R6, or R6 and R8, if any of those links went down, you'd have a valid backup path to get to where you've got to go. Now, the question that I have for you now is 9 and 10, do they qualify as a feasible successor? Now, we're calculating based off of R2, right? Because R2 is going where it's got to go. Even though R1 is connected to R2, R2 is the one that actually matters here because he is connected to 2 other routers besides R1. So the question is R9 and R10 valid? The answer is no, it's not. And you might say, well, how come? Well, if I'm on R2 and I look at R2 and I go, okay, my path from R2 to R8, if something happened to say this path right here, and everything else was down, well, technically it could be true. So I'd have 1, 2, 3, 4, 5, 6, 7. So I'd have 1, 2, 3, 4, 9, 10, 7, 8. That could be a backup path if the connection between R4 and R7 is down. And the connection between this path right here, R2 through R8, none of the links are up. Now, if R4 is good to go, let's say this is actually a check, and so it's actually there, would we ever take the path through R9? The answer is no, we wouldn't. And there would be no reason for traffic to go hit R7 and then for some reason go this way and then go to R10 to R9, then R9 to R4, then from R4 to R7. That would make no sense. You would never put yourself into a looping state in order for you to get to where you've got to go. So the answer to the question is only if, let me back this up a little bit, only if the connection between R4 and R7 was down and R4 was forced to go, which would make the advertised distance between R2 and R8 via 3, 4, 9, 10, and 7, if the advertised distance was less than the feasible distance end to end, then it would be valid. But if the advertised distance, if it had to go R4 to R7, R10 to R9 to R4 to R7, the advertised distance is going to be way higher than the feasible distance because you're having to go into a loop in order to get to where you've got to go. There's no point in that. It's basically the same concept of if you've ever driven in a roundabout. If you don't know what a roundabout is when you're driving, just Google roundabout. And essentially, instead of having a four-way intersection like this, where you come up to an intersection, you got stop signs or stop lights, and you would have to look left and right, and then you can proceed forward when you're or left or right. A roundabout allows you to keep driving as you're making your directional turn. So where I live, there's a lot of roundabouts. We have roundabouts everywhere. We have more roundabouts than I've ever seen. So the idea with the roundabout is, let's say you miss your turn and you end up having to go through the roundabout a couple of times. So you go through the roundabout once. The idea is if you need to go left, right? So I've got a roundabout here. If I come in this way into my roundabout and I need to exit over here, I need to go around the roundabout like that. Kind of a dumb design, to be honest with you. But what it does do is it keeps me moving. However, if I've got traffic, let's say traffic is coming from this direction, right? I have to wait because I don't know if they're going to come this way. So there's always there, because you have to yield to oncoming traffic. If traffic is coming towards you, then you have to yield, slow down, and look. If no traffic is coming, you're clear legally able to continue moving forward. Now, what happens if I am in this situation here where I'm like, oh crap, I was supposed to turn here. I didn't read my GPS correctly. Okay? Well, if I didn't read my GPS correctly, what would end up happening is if I bypass, I'd have to go all the way around to go back out again. That's where a roundabout comes into play. It has happened to me a couple of times when I'm driving and I get distracted, or I didn't read the GPS correctly, or there was a lot going on and I couldn't focus on what I needed to do. I've looked like an idiot a couple of times driving in circles, but that's where a roundabout comes into play. If you have to do a loop like this, if you have to come into here to go do this, you're never going to be a feasible successor. Why? Because you have to create a loop in order to get to where you got to go. That's my bottom line here. The key thing is, the key thing to remember is if your advertised distance is less than the feasible distance, then you're loop free and a viable backup. If your advertised distance is greater than the feasible distance, which means you have to go through more hops to get to where you want to go than the feasible distance is calculating, you are not a feasible successor. So just keep that in the back of your mind. This is not equal to, by the way, for basic logic. It doesn't compute. This is good. This is bad. So keep that in the back of your mind. So that's how that piece comes into play. I wanted to break that down so that you would make sure it would click. Because once it was explained to me like this, no problem. I understood. I never had to worry about it ever again. So that's how that comes into play. With that being said, let us carry on. All right, so we have some other things that I want to talk to you real quickly about in terms of how this all comes into play. So I don't want you to worry about too much about the serial number or the Cerno or any of that type of stuff, because this has to do with like serialized connections and things like that. We're never going to see serialized connections, at least in our environment, because of the fact that we don't deal with any TDM circuits, nothing that's time division. So you don't have to worry about that. So EIGRP does support different protocol suites. So IPv4, IPv6, and IPX, each of them with their own PDM, which is a protocol-dependent module. And so maintaining the neighbor and topology tables of EIGRP belong to the protocol suite. So you can look at the PDMs if you'd like. Building and translating protocol-specific packets for dual, so on and so forth. There's a lot that the PDM does. So we're going to see IPv4 and IPv6 when we do EIGRP v4 and EIGRP v6. We'll take a look at how that'll come into play. So don't worry about the IPX, because IPX is from Novell, and Novell doesn't exist anymore. I've never seen it in production. So that is the information you're going to need to consider when you're looking at the PDMs, stuff like that. Now, there are going to be details about the outputs that you're going to need to understand in order for things to make sense. So when you look at the show IP EIGRP neighbors, if I was to, this is all, we already have it running, so if I was to pull up, say, R61 and do a show IP EIGRP neighbors. Let me bring this down just a little bit so we have a reference. So just to go from left to right, top down. H, the list of neighbors in the order they are learned, starting at 0. So I've learned two different neighbors, 229, 61, 29, and 228, 61, 28. Okay? Now, what's going to end up happening here is you have the address, the IP address of the neighbor, right? The interface in which they were learned on, the hold time for the neighbor. If it gets to 0, the neighbor is down. The uptime, timer for how long the neighbor relationship has been up. So we're looking at a few hours. SRTT, this is the smooth round trip time, which is the time it takes to send and receive reliable EIGRP packets. Right now we're looking at 1 millisecond versus 1596. So I'd have to go look at my topology. I think 61 is an iOS XE box. 28 and 29, I believe, are iOS. So I'm not sure exactly why this one's so high, but not that important. RTO is the round trip timeout, which is the amount of time that the router will wait to retransmit an EIGRP reliable packet if an ACK acknowledgement is not received. The queue count is the number of EIGRP packets, update, query, and reply that the software is waiting to send. If you see a queue count, this is a bad sign. It indicates that there are packets waiting in the queue to be sent. If you have a scenario, and I had this happen to me not too long ago, where I noticed the RTO was very, very high and my queue count was growing. I'm like, well, that's not right. It turned out to be that the Cisco switch and the Cisco router that I was trying to form an EIGRP adjacency on, the MTU was incorrectly set. So the one side was sitting at 9. The interface MTU between the two devices was 9,000, but the IP MTU on the SPI, I think it was the physical interface that I was trying to form on, was set to 9,000. So I changed the IP MTU to be 1,500, and EIGRP came right up. So that does happen. So that will be a clear indicator. Or if you're trying to bring up adjacency and something else is hanging you up, just make sure that the queue count is clear. The sequence number. This is the sequence number of the last EIGRP packets being received from the neighbor. This is to ensure that the packets received from the neighbor are in order. The metric calculation. Now I want you guys to have a visual to see what that looked like. So I do not worry about this type of stuff right here. If I see it high, it's a lab environment. I really don't care. But you should see really, really low numbers in production on physical hardware. So just keep that in the back of your mind. When it comes to the metric calculation, we talked about this a little bit already, but I wanted just to take a few minutes and kind of dive into it. So the composite metric is K1 times the bandwidth plus K2 times the bandwidth divided by 256 minus the load plus K3 times the delay times K5 divided by the reliability plus K4. Okay, that's a lot to try to understand. Well, somebody that's really, really good at math, not me, came up with this formula. So now what's ironic is I believe in EIGRP it was the exact same calculation or formula, the exact same formula minus 256. So they needed to come up with a way to enhance EIGRP because it was EIGRP first, then EIGRP replaced it, and EIGRP added the multiplication of 256. So that's how it was able to scale. Now the K values, clearly we have 5 variables in the equation labeled K1 through 5 in addition to other variables like bandwidth, delay, reliability, and load. So again, these K values are nothing more than numbers 0 to 255, and the K values simply define how important other variables are. So by scaling them, multiplying them by an integer, then you can help them be more specific in how they do the calculation. K values are not equal to the variables they help scale. So by default, K1 and K3 are equal to 1, and K2, 4, and 5 are equal to 0. We can manipulate the K values with the metric weights EIGRP command. So the idea is this. If I go through and I adjust the K values, and I believe I can, if I do a show IP, is it show IP EIGRP? No. If I do a show IP protocols, it'll show me. Yes. So here we can say K1 and K3 are 1. Now, notice how they are single 1. Now, if I go to global config, I type in router EIGRP2, and I type in, what is the command? Metric weights. So I can come in here, 0 for type of support, K1. If I came in here and did K1, I did a 2, and then I did a K2 was a 3, and I did a K3 was a 1, I did K4 was a 6, and I did K5 was a 25, and then a K, I could adjust that. Now if I hit the enter key, we're going to see that the connections go down, and you're automatically going to see a K value mismatch. The other routers, 28 and 29, they're going to start freaking out. It's a K value mismatch. So don't do that. If you want to adjust your K values, you can do so. Now I'm going to go back to 61. I'm going to type in do show IP protocol, and we can see how we've affected it, right? Now the EIGRP metric calculation will be different. If you want to know more about this, I played around with it, so I'm kind of familiar with how it works. Go ahead and adjust all the K values to something other than their defaults, and you'll see how, I won't say wildly, but you'll see how EIGRP calculates the composite metric. I've seen some really, really big numbers, and I've seen some really, really small numbers. Now, can you turn a K value off that comes on by default? Yes, you can turn delay off. You can only do bandwidth. You can basically do whatever you want, but as long as you do it across the board. So just keep that in the back of your mind. So I'm just going to hit the up arrow, and I'm going to say no. So give that a moment to, and then there's my adjacency. Perfect. If I do another show IP EIGRP neighbors, and kind of ironic that my round trip timeout now is 100 and my smooth round trip time is down to 4. Much happier with that. So these are just some of the things that I wanted you guys to see in terms of how they work. If you want to, this is a reduction of the formula. So if you want to take a look at how this works, be my guest. Wide metrics, if you notice here, it uses basically the same thing, except for we replace some microseconds with picoseconds right there. And then you end up doing your bandwidth, instead of 10 to the 7 times 256, it's by 65536. And then bandwidth is now throughput. Throughput is K1, the EIGRP bandwidth plus the wide scale. Now, you have this new thing known as the rib scaling. This is a new way of looking at things. So iOS rib is only supports 32-bit metrics. After dual is ran, the metric is scaled down to fit the rib. So I believe it is a 64-bit value on wide metrics. Look, yeah, right here. EIGRP wide metric feature supports 64-bit metric calculations and rib scaling. So the rib scaling is so this what wide metrics really was available made to do was to give you higher speed connectivity, because the regular classic EIGRP metric calculation had an upper limit. I think it was like 10 gig, something like that. And then now that the interface speeds are much higher than that, you have to recalculate, and this basically gives it an infinite amount of scale. So the rib scale is the defaults to 128, and I believe it's the lower the number, the higher your composite metric is, and the higher the number, your lower the composite metric is going to be. I will play around with this because I can't remember which way it is, but nobody ever messes with this. I've never seen a customer go, "Oh, I want my wide metrics to be up here," so that it's this. Nobody ever talks about that. If we do enable it, it's there because we have a specific reason to, or I've had a couple of times where customers have been like, "Well, I'm studying for my whatever certification, and I saw it on the exam, so I wanted to try it out." Like, cool. If you want to turn your environment into a lab, be my guest. Like, I'm not going to stop you. So I'm like, okay, cool. Sure, what do we want to do? So that's basically how that comes into play. And there's a couple of additional ones. You got like jitter and you got energy, but I can't, I'm reading through here. I don't remember specifically what the driver, other than dealing with higher speed links, 25 and 40 and 100 gig interfaces. Beyond that, I don't remember why, if there was a specific reason or why wide metrics for the additional K values. Because like I said, other than the default bandwidth and delay, I've never ever had a situation where a K value needed to get added, like energy or jitter. No customer I've ever worked with has ever talked about that. Not to say that it won't happen in the future, but in most cases, you don't ever have to worry about that. At least I've never touched it. So maybe your experience is different, and if it is, awesome. Drop a comment in the comment section below. I'm curious to find out more, but that's basically how this comes into play. Now, what I'm not going to do is I'm not going to go through and really monkey around with this a whole lot, because we've talked about it, right? You understand how it works and stuff like that. So the key thing here isn't necessarily the metric calculation and being able to demo it in front of you. It's more or less, do you understand how it's calculated? You do. You understand that there's a K value, it's got a weighting factor to it, and stuff like that. But beyond how that comes into play, I'm not going to get into the topology table. Like, I mean, I could come in here and let me log back in real quick. I could come in here and go, whoops, not that, this guy. I could come in here and do a show IP EIGRP topology and then detail links, and we can get into the specifics, right? Well, so they do have a Cerno. Okay. You'll learn something new every day, right? So the feasible distance. Let's see. This is the same thing as all links. Yeah, same output. So the one thing you could do is you could sit there and you could say, for say 2.0.0.29 /32, and what it'll do is it'll give you kind of a breakdown where it says the composite metric is 138.16, 128.256. So you got to remember that your feasible distance is always going to be the number on the left. So your feasible distance is your best metric, and your reported distance is going to be, or your advertised distance is going to be 128,256. So if you take that into consideration, that's going to be how it's calculated. So you'd have to, if you take, math is not my strong suit, calculator. So we took 130,816, subtracted that from 128,256, 2560. So 2560 is our local distance. That's how much it costs to get from point A to point B. And then 128,256 is going to be our total distance to the destination. And I can't remember if 61 is attached to 29. It is. So if I was to look at this a little bit differently, let me zoom in here a little bit. And we look at 61, we'll look at 43. Let's look at 43 instead. The number is going to be a little bit higher. So here we have two different paths to get there. So we take, pull out my calculator again. We take this number here. We take 3097 minus 2841. We get a 256, right? So it's doing the job that we expect it to do. So 256 is what our delay is 21 microseconds. The reliability is 255. The load is 1. The MTU is 1500. So on and so forth. All those variables match based off of what we're expecting. So hop count is 2. So 256. So 256 plus 2841 is 3097. So that's how you would reverse engineer it. There's really not a whole lot to break down, right? So now that you've seen that, you understand how the composite metric is calculated based off the variables that we have available to us. If I was to go in here and manipulate other things, you'd see that those numbers change. So, but I don't really see any value in doing that, and I really have no way of bumping up the load or reliability to take it otherwise. So there's a question. So what is 255 out of 255? This means it's the most reliable it can be, and this 1 out of 25 is the least loaded it can be. So the most reliable and the least loaded. MTU, yes, you can affect the MTU. However, the idea with MTU is how much data is allowed to be sent in an EIGRP update, and if you manipulate that, both sides have to match on it. Because you might have a very big EIGRP neighbor table that you need, or topology table that you need to dump over to your neighbor, and you want to make sure you have enough MTU to handle that. So OSPF has the exact same thing, but they call it the reference bandwidth. How much, and there's another thing in here too you can do, router EIGRP 2, there is a metric, what's it called? No, I can't remember what it's referred to. There is a way to, I think I might be thinking about OSPF. There's a minimum amount of bandwidth that's can be done changing this, because it operates, there's like a QoS policy. If you ever look at QoS policy, was it type of service 6, I want to say? Something like that. I had to go look it up. EIGRP, no, that's not it. I can't remember what it is off the top of my head. But the idea is you have the ability of changing the, maybe, hold on, let me see if I can't find this real quick. Let's look up EIGRP bandwidth, control plane bandwidth. Oh, right here. This is it. I was curious on that. So the EIGRP bandwidth value, okay, that's not what I'm talking about. I'm talking about, EIGRP packets consume a maximum of 50% of the link bandwidth when configured with the bandwidth interface configuration command. For autonomous system configurations, the bandwidth percent command for name configurations. So if I was to look at this and look at the chapter contents, where am I looking here? Link bandwidth percentage. Let's see here. 50% of the maximum. Yep, let's minimize that. Let's go down here. So that is if you're doing metric weights, cost metric. That's that. A lot of this is going to focus on link bandwidth percentage, bandwidth percent command for interface bandwidth interface configuration for autonomous system configurations, passive interface. So I would do. Okay, so you'd have to go to the. So this is only supported in named mode, is what this looks like. Yes. So this is a named mode configuration only, is what it looks like. So you'd have to go, so this is going to be named mode right here. So you would go give it a name, then you go underneath the address family, and then underneath the address family, you go underneath the address family interface, and you'd set to bandwidth percent is 75. And what this would do is you would be giving configures the percentage of bandwidth that may be used by an EIGRP address family on an interface, and that's going to be sent EIGRP updates. So in other words, if I was to come in here and do, there is no bandwidth command, unless I was to go address family, IPv4, unicast, no, yeah, it wants me to go underneath the VRF. So I don't have named mode deployed yet. So if I did, I'd be able to. But if I was to go to interface a gig 1 and type in the bandwidth, this would be applicable. I could change the actual bandwidth of the interface down in the software queue. But you also have your bandwidth specific information for QoS. So, and we'll talk about that more in detail later and how changing your bandwidth on your interfaces can adversely affect your EIGRP metric calculation. So you would want to play with the delay versus your bandwidth. But now there's a question, how do I upgrade? So you can go to router EIGRP 2, and there's an EIGRP upgrade CLI command, and then you would give it a name. So you would do like, named, for example, and then when you do this is a one-way upgrade. So you can upgrade from non-named to named. And if you do this, it would automatically upgrade your configuration for you. So maybe I do this out of the gate. You know what, since I'm right here, let's go ahead and just do it. Configuration will be converted from router EIGRP 2 to router EIGRP named. Do you want to proceed? We'll say no. I'm going to change it different. I will, because yeah, you know what? I'll do it that way. Yes. So if I do show, it's the upgrade, the conversion's been done. So do show run section EIGRP. Now I'm in named mode. And when you change the named mode, you switch over to the address family unicast autonomous system 2 command. And then if we go underneath router EIGRP named, and then address family IPv4 unicast autonomous system 2, and then I can then go underneath AF interface, and I'll say gig 1, and then underneath here I'll be able to put in bandwidth percent, and then how much bandwidth EIGRP will be able to use. And you notice where it did a resync because I changed how EIGRP is calculating. So if I do a do show IP EIGRP topology, you're going to see some much higher numbers now because we're moving from microseconds to picoseconds now. And if I do show IP route EIGRP, my metric calculations are going to be a lot higher because I'm using wide metrics versus classic metrics. And the other thing, if I go in here and do show IP protocols, I am now using named mode, and so the metric version is 64-bit, and my rib scale, which is rib scale is 128. So if I was to come out of here and type in, I'd have to go underneath the that might be topology base, which is going to be the default VRF, and I would do, which one is that? Topology rib scale, where is that at? Nope, it's not underneath that one. It is exit out of here. Address family, IPv4, autonomous system 2, EIGRP. No, that's not it either. Where is that command? So if I look at rib dash scale, metric rib scale, that's where it's at. Okay, I wasn't too far off. So metric rib scale, and you'd be able to modify that. So let's do a 255. So do show IP EIGRP topology. Now the numbers are pretty high. So if I do show IP route, my numbers, they went up because before they were not this high. They were 129, or they're 129 now. Before they were 257, so they're lower. So the higher you go up, the lower the value is. Now if I was to do this again and do rib scale 1 and then do show IP route, my numbers are going to be really, really high. 3, that's a really high number. And if you notice, every time I do it, I flush the routing table. My adjacencies stay up, but I recalculate the numbers. So just keep those things in mind, that by manipulating the metric weights, by manipulating the K values, by manipulating your rib scale, things like that, you're going to adversely affect how EIGRP is going to calculate those routes. So that's what I wanted you to be aware of. So that's it for this video. I went a little further than I planned on, but at least gives you guys a solid idea of how it works and that type of stuff. So if you have any questions, comments, concerns, feedback, please drop me a comment in the comment section below. If you haven't already done so, please like, share, and subscribe, and I'll catch all of you fine people in the next video.